the next talk is going to be a bit complex. Actually, it's going to be all about complexity, right? And yeah, something that you might have heard if you're studying computer science, and then you thought, oh, what is this? This is so boring. But now we're going to find out about the exciting side of it.
Hi, everyone. So I'm Peter, and I want to tell you about big O notation. So a year ago, I remember being in talking with people and don't know how you start talking about development and code. And at some point someone says, oh, and then, yes, my algorithm was n squared 2. And I'd be like, okay, don't know what they're talking about. I'm going to slowly walk away. And this happened more and more. And I decided I have to do something about that. I want to understand what these people are talking about. And yeah, it seemed like a scary thing, something you need to study mathematics or computer science for. But I thought, let's just pick it up and see how far I get. And I discovered it doesn't have to be that hard. You can, like, the basics are understandable and can be used even in your own code or in your own problems. Yeah. And so what is it? What the big explanation is, it's a mathematical notation to describe limiting behavior, which I translate into the worst case. It's not really what it means, but good enough for me. About how an algorithm grows in memory or in time as the input to it grows. A lot of words. So I thought let's look at some examples. So again, the big O notation is because there's a big O, and then we have of what we can have a constant concept where nothing changes, and then we get more and more complicated. And as we can see, when the input grows, the time to run, if we use time here, the time to run it will grow. And depending on your big O notation, it will grow fast or not that fast. And I just want to go through some examples to make this easier. And I'll start with just O of 1. So a basic example is selecting an element from an array. We have an array A, which has some values. So how in memory, how do we look at that? We just say the location of this array is the location of the first point in the array. Now, if we want to get the first point, we just say, give me the 0th point of A. We take the location of A, add 0, and that location, we have our value, 8. The second, we do exactly the same. We add 1 to the location of our point, we get the 7, etc. It doesn't matter how big your array is. This always takes just as long to calculate. So that's a constant, O of 1. Now the next step, taking more time, O of n. Again, we're going to use the same array, but now we want to find where in this array is my specific element. We'll have to go through all elements till we find it. And as you can see, like if we want to see is 7 in this array, we start looking. First element, is it 7? No. Second element, is it 7? Yes. We say, we've got it, we found it, it's on position 1. But what if the element is not in there? Then we have to go through every one of them till we know, is it in there? So again, we have to loop through everything once, twice might also. We have to loop through every element, so that's an O of n. The next one, what about squaring? And I don't have the great graphs that we just saw, but I'm going to try and explain a bubble sort, a very basic way of sorting elements, which is a O square. So again, same element. And we're going to look at every value and compare it to the next value. So we start with just the first value. 8, is that smaller than 7? No, we swap them. Go to the next one. 8, is it smaller than 4? No, we swap again. And again, now we've done the whole thing, but we're still not in order. So we have to start over again from the first element. Is 7 larger than, smaller than 4? No, swap. Is 7 smaller than 2? No, swap. Is 7 smaller than 8? Yes. We do nothing, but we're not sure if our list is ordered yet. So we start over again. Well, you can see we do that one more time, but we still don't know, is our list ordered? The only way to know if our list is ordered is going through all of the values and seeing, yes, they are all smaller than the next one. So as you can see, we have to go through it 3 times 4, which close enough to 4 times 4 for this. So we call this an n of squared. We can do the sorting more efficient. We can do a merge sort, which will allow us to go through it n log n. What that means, this is because we do it in 2 steps. First, we have to go through every element, and then we can simplify it to go in less than the amount of elements through it. So the first step we do with a merge sort is split everything in the smallest pieces. As we can see, that returns 1 element everything. Now, these smallest elements we're going to compare with each other again. So we're going to compare 8 and 7. 7 is smaller, so we're going to put 7 first and then 8. We make this a new list. Next, we go to the other 2 and 4. We do the same. We check again which is smaller. Put that first. We make a new list. We have 2 lists now. One is 7, 8, and the other list with 2 and 4. And we're going to repeat this same trick. We're going to look at the first point of the first list and the first point of the second list. There we see that the 2 is bigger than the 7. We put 2 in our list. Repeat that. First element of the first list, first element of the second list. 7, 4. 4 smaller, 4 at the end. And as we repeat that, we again get our sorted list. But as you can see in the last step, we needed 12 iterations for this. Now we only need 9. So we were able to do the same kind of sorting in a faster way. The thing is, these like you never really get best of both worlds. So in the bubble sort, the time we need is the n squared, but the space we need to do it, we only need space for the swapping of 1 element. So that is a constant space. On the other side, for the merge sort, we can do it faster, but we need to make a copy of the whole list. So the amount of space we're using gets bigger. This is always it's always going to be a compromise. If you want to use more, if you want to use less time, you're probably going to use more space, and the other way around. Finally, I wanted to look through some like basic samples in your own code. I've done this in Python because that's what I use most of the time, but the principles are very similar for any language. So the basic thing, looping through a list, O of n, we just go through every element. But if we do a nested loop, we're going to n squared, because we're gonna for every loop of the first, we're doing a loop for the second. Then again, if you do 2 loops next to each other, don't do this ever, this code, but the basic idea, if you do 2 loops, you would get 2 times n. We ignore that first element, and this would just be an n problem. Some other examples. Sorting, really in any modern sorting algorithm will get you n of log n. You can always just assume that. Then I wanted to look at something, another way of like sorting things. And this is, for example, a heap queue. The big benefit of this is that if you would try and do this with just sorting, you would do n log n twice, while here we just do log n, which is even smaller than linear. So we're improving our speed. And these are things to think about. Are you sorting more than once? Maybe there's other ways of doing these problems. And I wanted to end with things like a set or a dictionary, a hash map in other languages, which can be very efficient in lookups, but in space, again, will have disadvantages compared to an array. And I kept it short. That was it. Some resources. The first one gives also practical examples of the big O notation, which with code there to make it easy to grasp for as a developer. The second one is a more general course really on data structures, but also has a good part on big O notations, and in general is just a good introduction to data structures. I want to thank everyone for listening.